Okay guys, I'm going to record a quick video here for the second half of class since I don't know that we're going to get the chance to get back in. But this way we can at least kind of keep going with our plan. So we've got a review question here. We're going to do parts A and B on the forest fire question, and then I'm going to add on a part C to review kind of our new skill for today. So we've got a forest fire and the number of trees burning at time t in hours is modeled by the function nt, and the fire is spreading at a rate of this. dn dt is 5 root t. So this is our prime, this is our rate of change, this is our essentially little f that we're given. I'm sorry. Okay. So if I want to know how many trees, what the change in number of burning trees is from time 0 to time 4, I'm going to integrate from 0 to 4, 5 root t dt. Okay, so if we integrate a rate of change from time A to time B, that gives us the total change over the interval of time. Okay, so one of the clues in this problem is it's asking for a change. All right, so number one thing, we figured out we're going to solve this problem through a definite integral, through an FTC application. And with little f being 5 root t, I'm going to need to remember that that's the same as 5t to the 1/2. Which means that big F is going to be 5t to the 3/2 divided by 3/2, or what'll ultimately be 10/3 t to the 3/2 plus c. And if we need a quick review, 5 divided by 3/2, 5 divided by 3/2 is the same as 5 times 2/3. A whole number 5 as a fraction would be 5 over 1. And so that's how 5 divided by 3/2 becomes 10/3. Or, you know, you can always check that on your calculator. But make sure that you're converting it back into a fraction and not leaving it as decimal. Okay, so capital F of 4 is 10/3. Ugh, that's a weird looking number. It's 10/3 times 4 to the 3/2 plus c, which comes out to be 80/3 plus c. Gotta love the 0 ones, because in most cases, f of 0 is 0, not all the time. Or it's 0, blah, 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 plus c. So we're not gonna worry about this problem. We'll continue for part A. My answer for that is 80/3, or I think that becomes like 26 2/3. And what were we counting on this one? We're counting trees. How many trees caught on fire between time 0 and time 4? 26 2/3 trees. So, you know, that's the mathematically accurate answer. In the real world, we'd see probably, you know, 26 totally in flames, and however you want to call something, like 2/3 on fire. So 26 to 27 in actual terms. In mathematical calculation accuracy, 26 and 2/3. Integrate a rate of change, and we get total change. Okay. That was our one style of problem. We did that over and over and over again for different intervals of change. Second problem. We have a starting value. If 100 trees are burning originally, so we have 100 at t = 0, we want to know how many we're going to have at t = 10. So we need to take our starting amount and our change and add them together. The starting amount and the change is what gives us a final amount. Let me grab this and move it to another screen. Where's that little toolbar guy? There we go. Okay. This whole thing. Oops, make him smaller. We'll just like erase him. We don't need him. That's not important. Okay, so I'm going to start with 100, and I'm going to add on the integral from 0 to 10 of my rate of change problem. Now, little f and didn't change. Big F doesn't change. So I basically just need to take my 100 and add on to it the difference between big F of 10 and big F of 0. So 100 plus, well, big F of 10. This is going to be a little messy. Because it's going to be 10/3 times 10 to the 3/2. That's a 1,000,000% calculator question. 10/3 times 10 to the 3/2 is like another 105.4-ish. So total trees. Okay. So we are at 100, starting with 100, and then the change between these 2 points is another 105. So the first type of total change problem is we're just calculating change between point A and point B, between this time and this time. Second change problem. With a starting point value together with a change, where do we end up? The change part of this is the 105. The final result is the 205. Now I'm going to add a part C in here. And I'm going to say, when will the number of trees on fire equal 150? So this is the when question. When is it going to happen? In a when question, we're going to set up an integral to calculate change, but I don't know when the change is going to stop. I'm going to start from 0 to some unknown x time. And if we think about totaling 150, we take that start, add on some unknown amount of change to figure out when we're going to get to the 150. So the change has to equal 50-ish. If I subtract 100 from both sides here, basically I'm saying, okay, I'm already starting with 100 trees. I start accumulating more trees on fire. I need to get 50 more to get to the 150. So I want to calculate how long is it going to take? What's that x going to have to be to make this 50? So we still think about little f. So we still think about big F. But this time it's big F of x minus big F of 0 equals 50. Or 10/3 x to the 3/2 minus 0, because we figured out that big F of 0 for the antiderivative is 0 equals 50. Now this is a fun one. We can graph again. We can graph y equals 10/3 x to the 3/2, and we can graph y equals 50 and find the intersection. Okay. In this one, and I know this will make some of you happy, we can also do some algebra. 10/3 x to the 3/2 equals 50. So if I do a little algebra here, I multiply by 3/10, x to the 3/2 equals 15. That's what happens when you take 50 times 3 and then divide by 10. And then a 2/3 power will eliminate the 3/2 power, or make it a 1. X to the power of 1 is 15 to the 2/3. And so we'll get that x is about, I take 15 to the 2/3, 6.08, I think these were hours. So about 6 hours in, we'll get about 50 more trees on fire, and we'll get to 150. That kind of makes sense with the 4-hour amount was like 26. So we know we had to go more than 4 hours. The 10-hour change was like 100. It's not the same amount of change every hour, so we can't just take, well, if I know the 4-hour change, I know 1 hour change, and then take it times 10. That will give you an estimate, but it will not give you the exact value. Once again, if you prefer, I don't know why my obsession with 50 today. So y equals 50, and then y equals 10/3 x to the 3/2. This is kind of a funky looking, oops, I didn't get an x, I got an asterisk. So there's the 50 that we still had, and then there's that function. And we calculate that intersection. And there's the 6.08. Okay, so we have an example now of finding the change, finding the final value from a starting value in an interval of time, and finding a time when we'll meet a certain value.